Hey guys, welcome back to my garage. Hey, I'm sorry I haven't done much in the way of videos lately. I've just been pretty busy and now getting caught up. This is the Fadal TRM update. I had this back panel on the bench running the DMM AC servos. Just to recap, I'm running Centroid oak. I'm using the GS3 DuraPulse VFD from automationdirect.com, and I'm using DMM Technologies DYN4 AC servo drives, and they're 1.3 kilowatt NEMA 42 AC servos. As of yesterday, I had a chance to get this thing wired up and basically running, moving for the first time since the conversion, and today I've got it running a program now, and I just wanted to share that with you. Let me see if I can zoom you in a little bit and kind of go over a few things in the cabinet. I see a lot of DYN4 users kind of going a little bit overboard with contactors and filters, line filters and line reactors and all that stuff. When you're talking about a kilowatt and less, I don't personally believe you need all that stuff. I followed the Centroid schematic, generic schematic for oak, and they have a number of them that you can refer to, which basically calls for one large contactor that's capable of the current that the drives are putting out. And then I used one line filter to feed the logic input to the DYN4 drives. So off that line filter there are 3 sets of wires coming from the filter. They're not daisy chained, they're paralleled here at the filter, they come down and they feed the logic power, which is L1 and L2 on these DYN4 drives. And then that in turn is being fed by a pair of fuses, and the logic power comes on when the control cabinet is powered up, just like oak. So it's ready to go, and the oak can start talking to the DYN4 drives. Now motor power is not brought on until oak is in the ready state. That means, you know, you've cycled the e-stop when the control first comes up, and you put oak online. So as soon as that's on, then the e-stop contactor closes and motor power is sent to these drives. Now my Z-axis, I have a brake on the spindle. I'll point you up there a little bit, and it's a DC 24 volt brake. Output 9 on the oak controls that brake, so until there's any motion called for on the axis, whether you jog an axis, whether you set home, or whether you go in MDI, the brake is not energized. So when it's not energized, the axis motor shaft is locked. But as soon as you call for motion, oak will automatically energize the brake, thus releasing the brake on the Z-axis. The reason for a spindle brake on that axis, or brake on the Z-axis on this particular machine, and actually any machines in general that have a ball screw and linear ways, they can fall without that brake. So you can't really put any kind of motor up there without some sort of axis brake to hold that Z in position when the servo motor is not energized and holding. So that's the reason behind a brake. I'll pan you up there in a second. I have a separate 24 volt DC power supply for that brake. It's not part of the logic to oak. It's separate. Let me zoom you in a little bit and we'll go into the cabinet in a little bit more detail. Okay, all my wire guides obviously are uncovered yet, and I keep them uncovered until I'm done completely with the cabinet, and then I tidy things up. There's no sense taking the covers on and off and that sort of thing until you're done with things. Like for example, I still got to get the pneumatic drawbar wired up, so I have to get a solenoid wired in. That really doesn't have anything to do with the control, but I will use 24 volt power off that power supply up above. So we're looking at the upper half of the cabinet again. This is the Lenovo Tiny. M92 PC. This is the Durapulse GS3. I choose the GS3 because it's a sensorless vector drive. Purportedly, they do much better at low RPMs, spindle RPMs with torque. This is the external 24 volt. It's a 2 amp power supply. It's a Meanwell MDR 60-24. It's more than enough to do what I need it to do. I have some fuses here. They're each pair. One pair is for the power supply, and the other pair is for and then there's two sets of fuses here. One pair of fuses is just for the spindle motor, and one pair of fuses is for the control and the servo amplifiers. Again, this is the line filter. It happens to be a 10 amp 250 volt line filter, so when this powers up, 240 volts is sent to the line filter, and then from the line filter to 3 sets of cables goes down to L1 and L2 of each DYN4 drive. And then down below here is my AC, my contactor. As I mentioned before, it's wired through the e-stop terminal on the Oak. E-stop, there's an e-stop output, and it's also wired through the e-stop button. So the e-stop button has 2 normally closed contacts. One that's in series with the e-stop contact closure on Oak, and the other one provides the e-stop signal to Oak itself. Over here, I left these items from the original Fadal cabinet. It's a very large line filter. And then here is an ABB. It's basically a start-stop switch. And then there are some Surresters, Surge Lollipops, I call them, up here on top. And I left all in. So power comes into the switch, drops down into the filter, out of the filter up to the fuses here. And again, these fuses, one's for the control, one pair is for the Durapulse, one pair is for the power supply, and then one pair is for the filter and the logic. That's what it was. Okay, so now I'll pan you down so you can see the filter, the lower half. Okay, here's the filter coming down from the switch, this line filter, of course. Here's the DYN4 AC servos. Again, L1, L2 is logic power, R and S is motor power. Those are coming from that e-stop relay and so forth. And we've got the data cables going into this DB25 and the DB9. And then these were provided by DMM Technologies. They use Centroid's data cables, and then they terminate it for you, and that's the best way to go, is let them do it. Now, there were several revisions of this, and I think I got these, boy, it's got to be the last half of 2019, the last quarter of 2019. So if you're a Centroid Oak user and your drives and cables were purchased somewhere before then, you might want to check with DMM to make sure you got the latest and greatest. Again, here's Oak. The logic power supply for Oak is underneath Oak itself. There you can see it poking out. There's the 3-axis data cables. This machine does not have a spindle encoder. It's not possible to put one on this particular machine, so rigid tapping is out, but the control still controls the spindle drive. I have a probe port on this. When we go to the front of the machine, I'll show you that. Ethernet connector for the shielded Ethernet cable to the Lenovo M92P. And then this is the terminal block. It's commonly known as TB1, terminal block 1. In my opinion, this is probably the best way to wire a cabinet like this is follow the Centroid schematic. Centroid did a good job engineering the schematics. It's proven. They have a number of schematics on their website. I just basically got a generic Oak schematic showing drives like this and following this. So basically the upper half of this terminal block is 240 volts, then a ground, a place for the grounds, and 24 volts, and then commons down here. This little fuse is a fuse for the e-stop contactor fuse. Otherwise, it's pretty straightforward. So you can tell that the cabinet itself is a pretty straightforward. It's very simple. This cabinet has a lot of room because there was a lot of stuff in it before, and this was the original cabinet to the Fadal machine. Here's the Z-axis servo. This is the connector for the brake. That motor has the brake built into it. These motors direct drive the screws. This Z-axis does not have a counterbalance, so that motor had to be large enough to be able to move this Z-axis up and down without issue. There is no cable carrier, the typical cable drag chain that you see on this particular machine. It doesn't need it. There's only 14 inches of Z-axis travel on this machine. Let's go around to the front. Okay, I want to start with the X-axis servo. So these motors made by DMM are standard NEMA 42 frame size. They basically took a metric frame motor, they enlarged the holes somewhat so they match the NEMA 42. And the shafts are machined. This shaft has a 5/8 inch diameter, and I didn't have to do anything. I could reuse the coupler and everything. Now the one thing about it's a good and bad, I guess. It's good that these shafts are actually longer than a standard NEMA 42 motor. So if you need the stick out for some reason, you actually get extra shaft. For me, it was a little bit of a problem, so I machined these spacer plates, and I'll show you a picture of them here. I machined the spacer plates because I didn't want to hack the end of the shaft off, so I just machined the plates. Now you'll notice here there's a little bit of an issue. I have these MS connectors standing upright on the motor on this X-axis because this motor travels with the table, and when they're turned down, they interfere with the saddle right here. They would hit. So at this time, I've just got them sticking straight up. I'm in contact with DMM to see if we can get a motor with their standard pigtails where they just come right off with a 90 connector, and then they just have pigtails, because these aren't going to work. I mean, they can work. It's not a problem, and they wouldn't be in the way. But I think I would, if I decide to keep them. There is a sheet metal cover. Here it is here. That goes like this. That just kind of keeps the swarf out of the coupler. I would probably box this downward to protect it, and it would kind of come up. It wouldn't be in the way of cutting, and certainly you could put a fixture plate on the table there. But that's kind of one little issue I've got right now. These cables will not stay like this. I'm going to put a piece of liquid tight flex. This is this Ultra Flex. I get it from McMaster Car. It's 1 inch. What I will do, let me grab a piece. Okay, here's a piece of that liquid tight flex. So you see my connector here, and then I'd have one on the back wall there. So this piece of flex would go here like so, right up against this. And as the y-axis comes out, this flex would roll out. And as the y-axis moves in the negative direction, the flex would roll in. So that shows the flex there, how that'll work out. And then the cables will be routed around and down and through that. The original Fadal actually had the cable running on the back side of the table and then down and into the bottom of the operator's control cabinet. Let me take you around to the y-axis. I forgot to show you that. Here's a shot of the y-axis. It's down at the base of the column and direct drives the y-axis ball screw. Pretty straightforward. There was enough room for these MS connectors here, so that wasn't an issue. Something a little unusual about this particular Fadal and a lot of the lower end Fadals, they don't have limit switches or home switches on them. Instead, you align marks, like here's the Z, and then on X you align the mark with the front edge here, and then Y you align the front edge of this truck with this mark here, and then you press cycle start to home the machine, and what the control will do is it will slowly turn the servo motors until the Z index marker pulse shows up and then stops it, and that sets home there. It's very repeatable provided you get these marks lined up before you set home. Mark Leonard on one of the forums had mentioned this idea is go ahead and set home and then get these marks to get the marks to line up precisely on all the axes after the control is found home. That way you can look at the markers, and when they're perfectly lined up, you know it's homed precisely. And then have a little bit of a gray area away from that marker pulse, so you know you have to get within that gray area before you press cycle start to home. But in any case, as long as that mark lines up with its opposing mark, then you know you've got home set precisely. The other thing that's different about this machine is it doesn't have a pressure lube system. It's a linear way machine, so the trucks actually have grease zerks on them. So you just lube the grease zerks. They're all pretty much accessible. Give us a shot of grease in these trucks and you're set all right. The other thing is that this machine had hand wheels. You may see them here both on X and Y. Z's gone because it was on the operator's control panel. But this was supposed to be meant for somebody who is transitioning from manual machining to CNC. You could actually turn these hand wheels and it would move the axis. I've chosen to use the Centroid wireless MPG to control all 3 axes and so forth. So no need to wire these up. They're going to come off and then the holes will get plugged. Right here is a bulkhead connector for the touch probe or the tool touch off probes. So with that brief overview out of the way, let's go ahead and run a simple program. I've just got the circular pocket program loaded. We can graph it. Simple program just to show you that the machine is running under Centroid control and driving the DYN AC servo drives and the motors. So on cycle start and okay, that's about it for this video. I just wanted to do a brief overview, catch you guys up where I was on the Fadal TRM. I still have to work on the spindle deceleration, it's pretty well calibrated. I've done all that, so it's pretty close to being done. I think you'll see a little bit more of this machine in some upcoming videos. So with that, you guys be safe during these times. Stay inside. Stay in your shops, stay busy. Talk to you soon.